working of aluminum alloy is essentially the result of applying sufficient force to the metal to cause permanent deformation. This is true whether the force is applied by hand, by hammer, or through machines of large load capacity, such as the drop hammer. These operations result in strain hardening or strengthening of the metal. The basis of this lies in the aluminum alloy itself. Microscopic study of a cross-section of an aluminum alloy specimen reveals a network formed by the boundaries between grains of the metal. Each grain is an accumulation of individual crystals or unit cells. The single crystal or unit cell is conceived to be cube-shaped with atoms of the metal arranged in regular order, one at each corner and one in the center of each face of the cube. These unit cells combine to form what is known as a space lattice. Within the space lattice, metal atoms exist in families of parallel planes with definite spacings between the planes. It is along these planes of weakness, called slip planes, that the crystal is most likely to glide or slip when deformed. These are important slip planes, along which movement may take place in the aluminum crystal. Through such movement, a crystal may undergo two types of deformation. The first is called elastic deformation. When small external forces are applied to the crystal, atoms on the lattice are moved slightly from their normal positions and the lattice structure is skewed. When the forces are removed, the atoms return to their original positions and the lattice recovers its normal shape. The second type, plastic deformation, occurs when the applied force is increased beyond the elastic limit of the crystal. The space lattice yields. In the process of twinning, the lattice is deformed by some fraction of an atomic spacing. In slip displacement, the blocks of atoms move an integral number of atomic spacings. When the external force is removed, the atoms are so far from their original positions that they cannot return. Plastic deformation is the basic process underlying the strengthening and hardening of aluminum alloys through cold working. If the force had been increased beyond the metal's ultimate strength, the crystal would have been sheared or ruptured. In sliding over each other in plastic deformation, the crystal blocks rotate, causing the crystal to become elongated. In tension, the crystal is stretched parallel to the axis of tension. In compression, the crystal is stretched perpendicular to the axis of compression. It is by this process that the metal grains become elongated and uniformly oriented when an alloy is cold worked. Essentially the same action is involved in the plastic deformation of the polycrystalline grains composing an alloy specimen. Before deformation, these grains are randomly oriented, and the slip planes for each grain are lined up in different directions. When a load is applied to the metal, the stresses are transmitted from grain to grain. Some begin to deform by slippage before others. Within each grain, the crystal blocks rotate to produce elongation. The deformation and rotation of any one grain is restricted by the differently oriented grains adjacent to it. These may also be rotating. Consequently, there is movement along the boundaries as well as along the slip planes. Each grain is now rotating, moving along its active slip planes toward the axis of tension or away from the axis of compression. The grains are now elongated and oriented in the direction of flow. Beyond this point, severe cold working may lead to more violent deformation, in which fragmentation and crushing of the grains occur. The total effect is to increase the metal's strength and hardness. One explanation of this effect is that disturbance along the slip planes and grain boundaries produces an amorphous material having no crystalline structure and therefore no planes of weakness. Thin layers of this material, stronger than the parent alloy, form along the slip planes and grain boundaries and serve as a cement to bolster resistance to further slip. Another theory, the fragmentation theory, states that during plastic deformation, minute crystal fragments break off and fall along the slip planes and grain boundaries. These fragments interfere mechanically with further slip by increasing the friction between crystal blocks and between grains. A third explanation, the lattice distortion theory, assumes that the crystal planes become bent and twisted during plastic deformation. The distortion of these planes and also of the lattice structure at the grain boundaries increases the resistance to further slip. The strengthening and hardening effects of cold working may be reduced or removed by means of the annealing process, which changes the metal to its soft condition, generally designated as SO. An aluminum alloy specimen that has been cold worked is in a condition of stress. In the annealing of a strain-hardened alloy, heat is applied to the metal. The initial effect is a partial removal of the stresses caused by cold working. At this point, grain size and shape remain unchanged. When the temperature is raised to a point called the recrystallization temperature, nuclei of new grains are formed from the fragments and crushed particles of the original grains. As the metal is heated above the recrystallization temperature, but below the melting point, these stress-free crystal nuclei grow into new equiaxed grains by merging with the other nuclei and by accretion of material from the surrounding stressed metal. At elevated temperatures, the new grains may become quite large. The alloy is now in its annealed or soft condition. When necessary, the strengthening and hardening effects of heat treatment may be removed by annealing. The solution heat treatment of an aluminum alloy such as 24S involves the further dispersion of the alloying element throughout the aluminum in minute particles and, following a rapid quench, the precipitation out of solution of some of the copper in the form of fine submicroscopic particles of copper-aluminum compound. In the annealing of a heat-treated alloy, the metal is heated at temperatures below the heat-treating range. The effect is to increase and accelerate the precipitation of this copper-aluminum compound from solution in coarse particles. This reduces the strengthening effect of the previous heat treatment. The alloy is now in its annealed or soft condition. Cold working or strain hardening operations may be undertaken for two purposes. First, to improve the physical properties of an alloy, cold rolling and stretching processes are generally employed. The second purpose of cold working is to form parts from alloys with strain hardening resulting from the operation. This involves such processes as bending, hammering, hydropress forming, stretch forming, drop hammering, and deep drawing. A pair of oppositely driven cylindrical rolls is the mechanical basis of the cold rolling process. A series of such pairs of rolls is used, the roll opening of each pair becoming progressively smaller. The passage of the ingot through successive pairs of rolls reduces the thickness of the metal. In the process of cold rolling, the equiax grains are flattened and elongated. The stretching process is based on the action of vise-like grips in which the edges of the aluminum alloy section are inserted. As the tensile load is applied through the grips, the metal is stretched, the equiax grains becoming elongated and oriented in the direction of the applied load. These grain changes increase the strength and hardness of the metal. For example, strain hardening caused by rolling or stretching a specimen of aluminum alloy 52S might increase the alloy's tensile strength from 29,000 pounds per square inch to 41,000 pounds per square inch, and raise the metal's Rockwell hardness number from H88 to H103. The primary function of the various forming methods is to convert the aluminum alloys into desired shapes. Strain hardening accompanies these cold working operations, and in extreme cases, annealing between operations may become necessary. Some forming operations require fully annealed or soft material. Operations such as bending may be performed by hand or by machine. This machine is used to bend metal sections that have already been formed, such as hat sections. Its basic operation is the passing of the part through a pair of rolls. As the part emerges, it is bent to the proper radius by a rubbing shoe, which is swung up to the required height. The power press brake may be employed to produce bends in aluminum alloy sheet. The ram of the press brake moves downward, exerting its load through the punch. The punch forces the alloy sheet into the die, forming the bend. Stretch press forming of aluminum alloy sheets is designed chiefly for the fabrication of parts with double curvatures. In stretch press forming, the opposite ends of a section of aluminum sheet are inserted into clamps. The die, located on a table midway between the clamps, moves upward, contacts the alloy sheet, and stretches it beyond the metal's elastic limit. The sheet is now plastically deformed to the shape of the die. Hammering is another forming method that may be done either by hand or with the use of automatic devices. The process of drop hammering capable of handling large parts and forming severe shapes with compound curvatures, may be performed with a rope-operated hammer or a pneumatic hammer. Hydraulic hammers are also used, but less extensively than either of the other two types. A desired part may be formed by a single blow of the hammer, the alloy sheet being shaped by pressure between the mated punch and die. For parts having deep draws or sharp corners, a series of blows may be necessary, involving the use of a set of progressive dies. The effect of hammering is to stretch the metal in one direction and to compress it at right angles to the stretch. The bending or shaping to double curvature of a number of parts at once is accomplished by use of a hydropress. The parts to be formed are loaded on a table, the alloy sections being placed on forming blocks or dies. The table is moved under the press, the action of which is single and continuous. The action of the hydropress is based on the use of a rubber blanket in place of the upper die. When it is brought down upon the loaded table, the rubber pad transmits pressure in a fluid-like manner, forcing the metal to the shape of the dies. Under the type of load applied in the bending and stretch forming processes, the grain structure of the aluminum alloy changes in a manner similar to that shown for the cold rolling and stretching processes. The grains rotate along the active slip planes and become elongated, and the metal is strain hardened. The cold working involved in the hammering, hydropress forming, drop hammering, and deep drawing operations results in grain rotation and elongation. But since the plastic deformation is generally more severe, fragmentation and crushing of the grains also occur. The fact that severe cold working results from such operations as drop hammering and deep drawing gives rise to the need for an annealing or softening process between blows or other forming operations in order to prevent rupture of the parts. In order to remove the effects of cold working and to soften the alloy for further forming operations, the strain-hardened alloy is annealed in an air furnace. Annealing is done at approximately 650 degrees Fahrenheit, and its effects are almost instantaneous. Annealing first relieves the internal stresses caused by cold working. As the metal is heated to recrystallization temperature and above, the nuclei of new grains are formed from the fragments and crushed particles of the original grains. These nuclei may merge with other fractured particles or with portions of the original grains, growing into new stress-free grains. The metal is now annealed and in a soft condition for further forming. If an aluminum alloy part has been strengthened through heat treatment and then strain hardened in the course of a forming operation, the effects of cold working and part of the effects of heat treatment may be removed by partially annealing the alloy in an air furnace. The partial annealing is performed at approximately 700 degrees Fahrenheit. The metal is kept in the furnace for about 30 minutes and then is quenched. The first internal change in the partial annealing is a relief of the cold work stressed grains and the recrystallization of the metal into new stress-free grains. The second change, resulting in partial removal of the effects of heat treatment, is the partial precipitation of the CuAl2 particles out of solution throughout the newly formed grains. The quench prevents this precipitation from becoming complete. Full annealing to remove the effects of both cold working and heat treatment, or of heat treatment alone, is accomplished by heating at approximately 800 degrees Fahrenheit for from 1 to 2 hours. The alloy parts are then allowed to cool slowly in the furnace. Once more, the first internal change is that of recrystallization, removing the effects of any cold working that may have been present. But this time, in the second change, most of the CuAl2 is precipitated out of solution in the form of coarse particles. The metal is now in the annealed or soft condition. Remember that in cold working, the physical properties of an aluminum alloy are affected by the deformation of the alloy grains. But in heat treatment, control of the physical properties is achieved by controlling the size and distribution of the particles of the alloy constituents. This is accomplished by solution heat treatment, age hardening, and annealing.